Thank you very much. So it's a great pleasure to participate in this very nice workshop. I will talk about phase transition in simple models of social agents. And well, I have to say right away that this is a relatively minor part of my research activity. And so I took seriously the suggestion by Jean-Philippe to do a kind of review of what I did over the last 10 or 12 years on this topic. So I will present a collection of different simple models. And I hope that there will be some interesting picture coming out of it. So, as physicists, how do we try to model social systems? Well, the traditional physicist viewpoint is that a human individual is modeled in a very simplified way as a social agent, which is a kind of social atom in the sense that it has only a few characteristic properties that are stable in time. So, like for instance, an opinion is not stable in time, maybe, but at least the agent has properties that are stable in time. And so this is certainly not realistic in general with respect to human beings who are complex, evolve in time, and so on. They are able to learn new things and so on. There may be also difficulty with the physics approach regarding the patterns that emerge, because these are often complex and heterogeneous structures like families, institutions, companies, or states, etc., which are difficult to describe in a simple way with a few global indicators like we do in physics. Nevertheless, the physics viewpoint might be very relevant to understand the collective behavior in cases where the behavior of human individuals is very constrained. So think, for instance, of an election. If you are at the polling place, you have a very constrained behavior because the only thing you can do is to vote. You can choose between a few possibilities, but certainly you won't read a book or drink coffee. So you have a very constrained behavior in this specific situation. So in this kind of situation, statistical physicists often postulate that ideas from statistical physics, meaning being able to describe an assembly of often identical particles that interact between themselves. So physicists postulate that this approach may be relevant to describe social systems, or some aspects of social systems. So in other words, the knowledge of this micro to macro procedure is assumed to be more important than an accurate description of individual, and we usually assume that details can be discarded for the description of individuals. Right, so coming to Anderson's paper, More is Different, I found a number of concepts or ideas in this paper which have been quite influential in my work. And I just want to emphasize 3 of them here that I will illustrate later in the talk. So the first one is obviously the emergence phenomenon in the sense that the macroscopic behavior may not be easily anticipated from the behavior of the individuals, the agents, or the particle. So the macro does not simply mimic the micro world. Associated to this, there's the idea of symmetry breaking. So a macroscopic system may not respect the microscopic symmetry of the particle, and it may choose one out of several possibilities. And this is really part of the emergence phenomenon. It's a way to distinguish a macroscopic system from the microscopic particle which fulfill the symmetry. Then I think another very important idea is kind of seeing the emergence as an iterative or hierarchical process in science. And so I just quote this part of the paper by Anderson, where there's a general idea that science X obeys the law of science, the elementary entities of science X obey the law of science Y, and this can be repeated a number of times. So basically, you start from elementary particles. From there, you go to condensed matter physics, let's say, and you can iterate the process many times. And if you really believe what Anderson is writing, you could go up to psychology, which is the building blocks of individual, and from that, the collective behavior would lead to social sciences. So, well, I don't know how far this should be taken seriously. But as a general concept, I think it's very useful. And at least for the first part of the interaction, I think it has been really influential in the last decade. So for instance, statistical physics in the last decade has gone a lot beyond the usual condensed matter physics in the sense of starting from atoms or molecules and going to matter at our scale. And for instance, people have been working a lot on active matter systems, which are made of, for instance, of biological cells or active colloids and so on. Also, there's been a lot of activity on granular matter, when individual particles are cent grains, for instance. So that's already a kind of second step in this iterative approach. Right. So in this view, I mean, this may suggest that a social agent may also be more complex than usually assumed. And maybe they could undergo some type of emergence inside them, right? They could have some kind of internal emergence that could be taken into account. So if I have time, I will come back to this at the end of the talk. Okay, so, well, just to kind of list the questions I've been trying to address on my research work on social agent model, they kind of follow what I've just picked up in Anderson's paper. So the first question is how much the collective behavior of social agents differ from that of a typical agent considered as isolated in some way. So what you would infer simply from the behavior of individual agent. Second is, well, okay, symmetry breaking is a concept very useful in condensed matter, but is it also useful or relevant in social agent model? And the last question is, well, can we increase the complexity of agent in some way to maybe see another type of emergence? And this is basically the outline of my talk. I will talk about 3 different models which follow these 3 questions. So before going into this, I would like just to have a brief reminder about what is a phase transition for non-physicists. So there are basically 2 different types of phase transition. The first one is discontinuous phase transition, like liquid vapor or liquid solid phase separations. And typically you have coexistence of 2 states. For instance, if you are at a temperature of 0 Celsius, you could have coexistence of ice and liquid water in your glass. And the second type of phase transition is continuous phase separation, which is the one associated with spontaneous symmetry breaking. So typical example is a magnet. So you can imagine a magnet as made of a large number of atoms. Each atom carries a smaller row, which we call a spin, but it's like a very small magnet. And these rows can be aligned in a random direction. Well, let's say only up or down, but if they are arranged in random directions, so the global magnetization is 0. So this is what happens at high temperature here. And when you lower the temperature, due to interactions, you have the onset of a non-zero magnetization, which can be either up, like this, where most spins, most rows point upwards, or negative magnetization corresponding to arrows pointing downwards. So these 2 states are completely equivalent, but the system has to choose one of them because it cannot be in the 2 states simultaneously. For a large enough system, it is no longer able to switch from one macro state to the other. So this is a phenomenon of symmetry breaking. There are 2 or several states that are equivalent, and that are all possible, but the system has to choose one of them, and in a reasonable time, it cannot switch to another one afterwards. Okay, so, so we start with the Schelling model, which is a very famous model for urban phase segregation. And so the model situation is a very schematic city where agents move in flats and live in flats and can only move from one flat to another. So we're interested in the dynamics of how agents move from one place to another in the city. And so there are several goals or aims in this model. So the first one could be to be able to determine the equilibrium distribution of agents in the city. More on the sociological side, one could try to understand possible origins of the segregation phenomenon. And also, as we will see, we would like to compare the collective and individual behavior. So what happens at the macroscopic scale as compared to the individual scale of agents. So the model was introduced in 1971 by Schelling, who was an economist. And so this paper became very famous, but it turns out that a very similar and actually more general model was published in the same year in the same journal, and actually in just the previous issue, by another researcher called Sakoda, but unfortunately he became much less famous. But okay, it could be called the Sakoda-Schelling model. So the idea is to consider, to represent a two-dimensional city as a checkerboard or a two-dimensional lattice. Each square of the lattice is a flat, and it could be occupied by two types of agents, so red agent, green agent, and if the flat is white, it means that it's empty. So each agent has a satisfaction degree, which is called utility, and which is associated with a satisfaction about the composition of the neighborhood. So you may like, the agent may like to have a similar agent in its neighborhood or a mixed neighborhood and so on. So the model has been simulated numerically quite a lot in many papers, and so typically one observed a phase separation, so a type of segregation between regions dense in red agent and regions then in the other type of agent.
Can move to anywhere in the square?
Yes, so it's long range, yeah. You can move anywhere in the city, yes. Okay, so from a statistical physics standpoint, it's also interesting to try to see how much the method, the approaches of statistical physics can be generalized to such particles which are selfish in the sense that they consider only the variation of their individual utility. They don't care about the implications that their move has on other agents. So that's interesting from the methodological standpoint. So now technically the difficulty is that the standard Schelling model cannot be solved analytically, so we can only do numerics. And so what we tried with collaborators in Lyon at the time, so Pablo Jensen mainly, we tried to simplify the model in order to be able to solve it analytically. So the first type of simplification is to consider a single type of agent instead of two types of agent. And so segregation would be replaced by a phase separation with dense phase and a dilute phase. And also we simplified, a key simplification was to simplify the geometry, meaning that we divided the city into blocks, and we considered that the neighborhood of each agent is simply the block in which it lives. So there are no overlaps, no partial overlaps between the different neighborhoods, and this is the key to find an easy solution to the model. Right, so just to define the model a little bit more precisely, so we have now a city which is divided into blocks, so number Q of blocks. Each block is composed of a number H of a square, so of flats. And so we assume that both Q and H are large, so there are a large number of blocks, and in each block there is a large number of flats. We introduce a number NQ of agent in a given block Q, and the utility is assumed to be a function of the density in the block in which the agent is. So dynamical rule is very standard, I mean the same as in the original Schelling model. So it takes this form, which is familiar both to physicists and to economists. So for economists, this is basically called the logit rule. For physicists, it's something similar to the Glauber transition rate. So what appears here is a variation, the change in utility between the target flat and the current flat. So yeah, the original Schelling model was studied mainly at 0 temperature. Here we have a temperature, which is not a true physical temperature, but a parameter that introduces stochasticity in the dynamics, meaning that from time to time, an agent will move even if this decreases its utility. So in economics, this stochasticity is justified by the fact that some of the preferences of agents are not taken into account explicitly, and this introduces some stochasticity. This is not supposed to be really same type of stochasticity like thermal fluctuations in physics, but okay, this is just a matter of interpretation. Right, so now we need to, to proceed further, we need to choose a specific form, a simple parameterization of the utility function. And so we chose this very simple form, which is piecewise linear. So the density is between 0 and 1. Utility is also chosen between 0 and 1. And we considered agents that would like very much to have a mixed neighborhood, so they are very happy if their block is half filled. So it corresponds to a density of 0.5 here. But okay, there's a parameter m here describing the asymmetry of the function. So here, when m is positive, it means that they're happier if the neighborhood, the block, is completely filled than if it is completely empty. So now the question is, okay, let me take a city where the average density is 0.5. In principle, all the agents would be happy with uniform distribution in the city. But is it really what one observes? Meaning, is the collective behavior really the same behavior as that of a representative agent? So actually, the model is simple enough so that you can compute the distribution analytically. And so distribution is a joint distribution of all the densities of the blocks. And it can be expressed in the simple form of the exponential of a sum of some function of the density of each block. So here, technically, it is simple because the model obeys detailed balance. So really, it's just like an equilibrium model in statistical physics. And here, the interesting part is that, so this effective free energy that appears here in the physics language can be expressed as the sum of a term which is a primitive, an integral of the utility function, minus an entropic term. So the entropic term is the usual one, like in physics. But so this term here replaces the usual energy in a physical model. And so you see that it's not like one may have expected simply the opposite of the utility, because one often thinks of the utility as minus the energy in physics. But due to the fact that agents consider their own utility only during the moves, it makes this important difference that the integral appears here. Okay. So what happens in practice? This is just a sketch of the function f of rho, so this effective free energy. And if you are at an average density rho 0, for instance 0.5, you will see that this function f of rho is actually non-convex. There is a concave intruder here. And so the most probable configuration corresponds actually to a phase separation between low density phase here and high density phase. Okay, again, this is just a sketch. It's not the true function appearing in the model. So there's phase separation between the dense phase and the dilute phase, meaning that agents are not really happy by the outcome of the collective dynamics because they would like to have a mixed neighborhood, but actually they end up in situations which are not optimal. So now, well, the question could be, okay, what if agents take at least partly into account the effects, the consequences of their moves to other agents? So we have slightly generalized the model by taking into account the cost, GI here, which is a sum of the utility variation of agent I here, plus the sum of the variations of other agents, but with the parameter alpha, so which is typically less than 1. And this could be interpreted either as some kind of altruistic behavior or as a kind of tax imposed by a state, for instance. So alpha equals 0 corresponds to the previous Schelling model. Alpha equals 1 is exactly what happens in usual physics model with the interpretation that U would be the opposite of local energy. So we have plotted on this color map the optimality of the collective outcome, the collective behavior that is observed. So there are two control parameters. There's here this parameter M that controls the asymmetry of the utility function. So I will stick to the case M equals 0, so a symmetric utility function. And you see that for alpha equals 0, so as I was talking previously for the Schelling model, the collective behavior is far from optimality because you see that the normalized utility is about 0.6, so 60% of the optimal value. Increasing alpha, this normalized utility increases, and beyond some intermediate value alpha c, which is less than 1, so it's about 0.5, I don't know the exact value. Beyond this, above this value, actually the collective dynamics recovers the optimal state. So it's interesting to see that you don't need to go up to alpha equals 1 to reach an optimal state. So now we have tried later on to generalize this model by mixing actually the two types of agent. So for instance, you could consider that you have a large fraction of selfish agents, so the usual ones of the Schelling model, which with alpha equals 0, and you include in the model a tiny fraction of, say, altruistic agents with alpha equals 1. And what we observe is a kind of catalytic effect of this altruistic agent, which allow, with a really small fraction of such agent, to recover an optimal state. So the mechanism is illustrated on these plots. So what happens is that, okay, so the yellow agents are the altruistic ones. You have a lot of empty blocks, as in the usual Schelling model. But actually, these yellow agents, these altruistic agents, they don't care too much about having an empty block. And so, by some fluctuation, they can start to gather in some empty block. And actually, these fluctuations get amplified, and so they populate more and more one block, chosen at random. And once they overcome a certain density, then this block becomes attractive for a usual selfish agent, which now come massively populate this block. And so then these altruistic agent, this yellow agent, they move on to another block where they start doing the same thing. So block by block, you can repopulate in a more or less uniform way the city. And so to make the analysis more quantitative, we have plotted again this normalized utility value. And you see that with very small fraction p of the altruistic agent, so of the order of 10 to the minus 3, 10 to the minus 2, depending on system size, you are able to recover the optimal state. So meaning a uniform distribution of agents in the city. So when you vary system size, you see that actually the threshold for optimality decreases, and it actually scales like 1 over q, so 1 over the number of blocks. And if you rescale the data by plotting p star equals basically p times q, you see a nice collapse. Okay, a last point on this type of models is a question about what would be an indicator, a uniform indicator in phase-separated systems? So this is quite a natural question for physicists, because when you have a phase separation, you know that the chemical potential is uniform throughout your system, so it's equal in the two phases, and it's a typical way to compute the densities of the two phases. You can ask, okay, is there something similar in this socioeconomic model? And actually, economists tell you that if you're at zero temperature, you should reach a Nash equilibrium, in which case all agents maximize their utility, and so the utility should be uniform throughout the system. So the question was, okay, can we make contact between the two viewpoints, and also can we generalize this notion of Nash equilibrium, or at least the resulting utility that equalizes everywhere, can we generalize this to a non-zero temperature, to a positive temperature case? And so actually we consider a class of model which is a generalization of the Schelling model, so with the same idea that the city is composed of blocks, but with more general rules. And within this class of model, we could show that we can compute, using the same rules as in usual statistical physics, we can compute a chemical potential that is equal to the typical utility of agent as at zero temperature, plus a temperature contribution, which is non-zero when temperature is non-zero, which is proportional to both temperature and to the derivative of the local coarse-grained entropy in the system. And so we actually tested this prediction in a model that was actually not in the class we used to derive the definition. We considered a model of an inhomogeneous city with a business center. And so there's a cost of traveling, but also a cost of housing, which differs depending on the distance to the city center. And you see that, so okay, on this graph, so you have here the distance, normalized distance to the center. And here we have plotted two quantities, so the utilities here and here. So the colors, the blue and red colors correspond to different values of temperature. So let me look, for instance, at the red data. We have plotted here the utility as a function of distance, so what you would look at when considering the Nash equilibrium. And we see that this utility is not uniform at non-zero temperature. It has some spatial dependence. But when you take into account this correction and compute this effective chemical potential, you get this curve. And so you get an indicator which is uniform within the system. And so the same is true for different temperature in blue. Okay, so we thought this was an interesting contact between statistical physics idea and socioeconomic ideas. Right, so now I will move on to a different model to address the issue of spontaneous symmetry breaking. So here in the discrete choice model. So it's a model about agents who have to choose products that they buy in two different stores. And these stores sell fresh products which can age if they stay some time in the store. So in principle, the stores are equivalent. Let's say they are the same distance for the customer, same price, etc. So only the freshness of the product may differ. And so in principle, since both stores are equivalent, there should be the same flux of customers in both of them, so same number of customers coming every day to the shop. So just to have a slightly more formal definition, so again, we have two stores selling perishable goods. These goods are replaced by fresh ones once they are sold. They are immediately replaced by fresh ones. And we define quantity H, called the freshness, which decays exponentially with the age of a product. So the age is 0 when you replace with a fresh product, and then it ages and becomes less fresh. So there's a natural control parameter in the problem, which is the ratio of the typical time for a product to be sold and this characteristic time tau f appearing in the definition of the freshness. So if R is small, the products are often renewed and they remain fresh. If R is large, there is not enough customer flux, and the freshness of product become low. So one can simulate. Okay, so dynamics is very similar to what we take in the Schelling model or other types of socioeconomic model. It's still the logic rule. So here the utility is actually the difference. Okay, so delta S here is the utility difference between the satisfaction of agents with respect to the two shops. So let's say that agents randomly go to each of the stores, and they have a memory of the freshness of the products they bought previously. And due to this memory, they have different satisfactions about these two stores. So they make the difference, and they choose, according to this rule, to which store they go buy a product. So if you do a numerical simulation of the model, you see that after some time, you have a symmetry breaking. So initially, so what is plotted here is the average freshness in each of the stores. So initially, they are equal. And after some time, actually, most of the customers, most of the agents go to the blue store, and they don't go to the other one. So the freshness of the green store decreases a lot, while in the blue store, the product becomes fresher on average. The model is simple enough so that one can analyze analytically the phase diagram in the parameter space R and T. So T is, again, the temperature in the logic rule. R is this control parameter, so ratio of the two time scales. And you find basically two domains in this phase diagram. So this is quite expected that at high temperature, there is no symmetry breaking, so the two stores remain equivalent. At low temperature, there's a symmetry breaking, so one of the stores is more visited by customers. And there are some subtleties in this area here where there are some metastability issues, so one or the other of the two states may be metastable. So later on, we came back with other colleagues from Korea. We came back to this model and said, well, okay, so there's in principle not only the freshness, but we should also take into account the price. And the idea was that, well, if the products are no longer fresh, maybe the price should decrease. And so we introduced this further ingredient in the model that when the freshness is very low, the price decreases. And so now the satisfaction of the agent is a weighted average of the freshness of the product and of minus the price. So they are happy if minus the price is high, the price is low. And okay, so taking into account these two ingredients, now we observe some oscillations. So different types of oscillations here. So what is plotted here is a probability to go to one of the stores. So for instance, in red is a probability to go to the first store. And you can see large oscillations like this where people really change. The majority of agents change of store periodically, or most of them still go to the same store, but with a strong oscillation in this probability. Okay, in the last maybe 5 minutes, I will talk about this idea that there may be two levels of emergence, so considering more complex agents. So we may like to increase the agent complexity. Well, so in principle, we may like agents to be able to process some complicated type of information, but I don't go to such complexity here. I just want to have a minimal kind of complexity, which is to have agents with a large number of internal configurations. And so the motivation is that with this further degree of complexity, it would be possible to have two levels of emergence, maybe. One inside each agent, and one in the collective behavior of the population of agents. So, I introduced a somewhat abstract conceptual toy model with agents having a large number H of configurations that I call C. So a large number of internal configurations, and so most of these configurations are equivalent and have no kind of featureless. But some of them, two of them have a specific property, which is like a spin. And so let's say configuration C equals 1 has a spin equal to 1, and configuration 2 has a spin equal to minus 1. So meaning that there are two configurations only out of the H configuration that have specific features, and these two are equivalent but distinct, and so having 1 and minus 1 allows for a kind of symmetry breaking analysis. So I need to define the utility of agent to allow for some type of dynamics of the logic type, as usual. And so the utility which is chosen here includes two terms. So there is one term with two different coupling constants. There is one term which favors, moving to the configurations which have a feature, so this non-zero spin, let's say. And the second term here favors symmetry breaking. So this is like what you would have in the kind of Ising Hamiltonian. And this is that allows you maybe to select the internal configuration which have the specific feature, so non-zero spin. So the important thing now is to introduce two different order parameters, which correspond to the two types of interactions I was just mentioning. So a first parameter is Q, and it's the normalized sum of the absolute value of S. So it means that when Q equals 0, agents are typically in a featureless state. They have no characteristic. And when Q is non-zero, it means that a finite fraction of the agents are in this state with a non-zero spin. The second order parameter is a magnetization, like in the Ising model, so it's just the sum of the spin, and so it allows you to distinguish between symmetric space and symmetry-broken space. So now, again, the model is simple enough so that you can analyze it analytically. You can derive some result analytically. And so I plot here the two order parameters, Q and M, actually absolute value of M. And so you observe two types of transition. So the red curve here corresponds to the transition on Q, which I call a standardization transition. So it means that at high temperature, so above this temperature Ts, agents are in a randomly chosen internal configuration, and so most of them don't have this characteristic. So they are essentially featureless, and so if they are featureless, they are not able to have a global magnetization. So when you decrease temperature, you reach this temperature Ts, above which actually all agents, because you have discontinuous transition here to a value which is very close to 1, essentially all agents now have this spin that appears, so a non-zero spin, so either 1 or minus 1. And so it means that agents that were initially complicated because they had many possible configurations, they kind of collapse in a simple state where only two possible configurations. So it's a way to have a standardized agent which are simple out of initially complicated agents. And so once you have this standardization of agents, so each one now has a spin, you can have the usual Ising type emergence of a magnetization here. So you have two different emergence again. So the internal emergence inside agents here, and the second one, which is at the collective level, so symmetry breaking in the population of agents. Now here I assume that Ts is larger than Tm, but the other situation is also possible depending on model parameters. And so if you're in a regime where Ts is actually smaller than the expected Tm, you have nothing actually happening at Tm. You need to reach Ts to get the standardization transition with the appearance of spins for all the agents, and then the magnetization jumps discontinuously to this non-zero value here. And then you have the usual curve. So I think I have to stop here. I just want to mention very briefly that I also proposed recently a generalization of this abstract model, including disorder, so it's inspired by the random energy model. You can include random quench idiosyncratic utilities in the model. And then you have two different types of standardization or simplification. So you may have complex agents where there are in any of these many internal states. You have the simple homogeneous agent, like the one which had a spin plus or minus 1. And you have another type of simplification which is driven by the disorder. And so actually each agent is kind of stuck in a configuration, but which is not the same as the other agent. It's just frozen there, just as in glassy systems. Okay, so yeah, to conclude, I just wanted to illustrate in simple models some important ideas that were put forward by Anderson in More is Different. So the fact that collective behavior may not be simply extrapolated from the individual behavior of agent. The importance of spontaneous symmetry breaking beyond condensed matter and in social agent model. And also a kind of hierarchy of emergences phenomenon. Voilà. Illustrated the possibility of two levels of emergences. I just would like to end up kind of advertising kind of orthogonal approach, orthogonal type of discussion by Pablo Jensen, my collaborator in Lyon, who is discussing the political implication of simple models. So I had a very favorable view on this simple model. You can also have more critical views and discuss possible political implications. And so you may read this paper here if you are interested. Thank you very much.